Okay, so now we've established all of the equations that express uniformly accelerated motion. What we'd like to look at is the graphical representations of uniform acceleration, and that is to say that all of the equations that we have looked at and we just summarized can now be seen in the graphical versions. So we're going to mostly focus on the position time, or we could also call it the displacement time graph, or even the distance time graph would be okay. And look at the equation that goes with the displacement time graph. Well, if you think back to the summary of equations, to an equation which had both displacement and time, there were a couple of choices. It really was these two are my choices. Now, if I'm thinking about the displacement versus time graph, I really would want to focus on this equation right here. This is the equation that would show up if I were to graph the displacement versus the time. So let's write that equation here at the top, and we can write it one of two ways. We can either write delta x equals 1/2 at squared plus v naught t, or maybe even a better version of the equation would be to break up the delta x, which you know would be x minus x naught, and take the x naught over to the other side, and then we would get an equation that will tell me the displacement at any time based on knowing the acceleration, the time, the initial velocity, and obviously the initial displacement or the initial position. So this equation is the equation of the line that I am about to draw. So let's make a displacement time graph. Let's move this up just a little bit. And let's make a couple of axes. We're not going to put any numbers on this. We're just going to sort of create some nice uniform axes. Okay, so on this axis we are going to put time. Let's just put it here. And on this one we're going to have x. And we're just going to focus on the positive side of this equation right now. Now, it should be pretty obvious to you that this equation is a quadratic equation. And if you could sort of mentally visualize what the shape of a quadratic equation looks like, I hope that right now in your mind you're visualizing the shape of a parabola. So this is a parabolic curve, we would say. Now, we will oftentimes refer to these curves as a line. So in math class, that would not technically be correct, because a line refers to a straight line, as I've drawn on the axes here. But in science, when we think about the line that describes the motion, or on any graph, everything is a line. Everything is a line, whether it curves or whether it goes straight. If I want to specify that I mean a straight line, then I would actually say a straight line. So line is a generic term that can refer to things actually that are curved, but that is a continuous line. So in the case of this graph would look something like, let's do this. So flat at first, and then with an increasingly steeper and steeper slope to it. So it would end up something like this, and let's see what things that we can see off of this graph. Well, the first thing would be right down here where we're looking at time equals 0, the location here where this meets the y-axis, this is going to be my initial position. Okay, now we have to think about how do we get some of the other properties off of this thing. Obviously x, we can read off the axis, t, we can read off the axis here. How do we get the initial velocity? How do we get velocity in general from this graph? Well, let's remind ourselves, for the displacement time or the position time graph, the way that we get the slope, or get the velocity I should say, is the slope. Okay, this is not a general statement. We can't say this for every graph. It's specific to this graph. For the displacement time graph, the slope of the graph equals the velocity. Now, in the past, it was a little bit easier because we had straight lines. So we would calculate the slope one time, and we would be done, and that was it. We had calculated the velocity effectively for all time. But in this case, you can see that we have a changing velocity. So let's make a note and this is for the uniformly accelerated motion, a changing slope means changing velocity. For this specific example, what's happening to the slope, and let me get something to sort of illustrate the slope. So I'll try to put this on the graph, and you can see that down here the slope is very flat. If I match up this paperclip with the slope, you can see here it's very flat, but if I follow as time goes on, you'll see that what's happening is that the steepness of the line is increasing. And that should tell you, and you should think in your mind, what exactly then is happening to the velocity as time is going on. We start off with a very flat slope, and then as time goes on, we're getting an increasingly steeper and steeper slope, which means that we are getting an increasingly larger velocity. The velocity of this object is increasing, and if we go all the way back down to the origin, we can make a note here. At the origin, the slope equals V naught. Okay, so the slope of the line will give me the initial velocity of this object. And all I would need to do is to calculate the slope of this thing. Now, if you think about it, this is going to be pretty challenging because in the past when we had a straight line, we could just pick any 2 points that we wanted to. But for example, here I cannot just pick 2 points. I cannot just pick a point here and a point further down and calculate the slope, because what I would be getting instead of the velocity at a particular instant is I would be getting the average velocity. I would get the average velocity, which may not necessarily tell me the velocity at any particular time. So you can imagine that if I have a point here and a point here and I connect those two, that this would only give me the average velocity. So let me pick 2 points and let's connect those with a straight line. Now I could use those 2 points to make a velocity calculation. It will absolutely work. I'll have a change in position or change in displacement over the change in time. However, this line would only represent the average So if you can imagine drawing a line down here, we'd have T1 and T2, and it is not that this line doesn't give me any useful information. It would tell me the average velocity between those 2 points. So if you remember, we actually had that in a previous equation. We used that. Here is the average velocity for an object which is changing its velocity. We add the 2 velocities and we cut them in half. Well, that's essentially what we are going to be doing here. We're going to be getting the average velocity of the two between those 2 points, or between those 2 times. Now that's not particularly useful. Let's say if, for example, that what I wanted was I wanted the velocity at this point right there. Well, the trick to that in this case is that we need a line drawn on this graph which has the same slope as the curve has at that point. Now if you think about a line which would have the same slope as the curve, that line is called the tangent line. So to find the slope, or I should say to find instantaneous velocity, we use something called the tangent slope method. Okay, and essentially the way this is going to work is we're going to somehow have to use our ruler in order to figure out a line, which again, the whole purpose of this method is, although the line is curved, you could imagine if I could zoom in and look at just this little tiny point on the graph, just this tiny little section of the graph on either side, that line, as I zoom in, is going to appear to be straighter and straighter. Just in the same way as if you look at a picture of the Earth from outer space, the Earth looks obviously curved. It's very clearly a sphere, but as you get down closer to the surface of the Earth, it looks less and less curved. So this is the idea behind this. If you could imagine looking at a tiny section of this line, it would look pretty straight, and we could calculate the slope of that line. But we're not looking at a tiny little section of that, so what we need to do is to create a longer line that we can see that's going to have the same slope as the curve has at that particular point. This is the whole idea behind the tangent slope method. So what I'm going to do is I'm going to adjust my ruler, and I'm going to keep looking. For example, here it's a little too steep, and then up this way it's a little bit, I'm sorry, this is too shallow, my mistake, and this is too steep. So I want something that's going to balance. Now, truly a tangent line should actually touch the curve in one point. But I'm going to tell you a secret to this method is to make the line tangent in that it has the same slope, but don't allow it to touch the curve, because if it touches the curve, that's going to make it difficult for us to see the tangent line compared to the curve. It's going to be very hard for us to pick points off of this tangent line. So we will make a line that's tangent, has the same slope, but we're going to do it in such a way that it's slightly out away from the curve so that we can see the points a little bit more clearly. So I feel like that's a pretty good match for the curve. And so now I would draw my tangent line. So this is my tangent line. Tangent line at t equals t3. So we're going to have a third time here. And my goal is to figure out what the velocity, at t3, my goal here is to figure out what is the velocity of the curve at this point. So here's the curve, here's my tangent line, and you can see that's a pretty good match. Okay, if I'm looking at the curve right here, these are pretty straight, except the difference is this curve's away in both directions as I move away from this point, but the tangent line does not. The tangent line stays nice and straight. So at this point, what I would do would be to pick 2 points on the curve, and I would I would calculate my slope. So I would use my change in x over my change in t to calculate the slope. And here's the thing. I'm actually calculating the slope of the straight line, but I know that the slope of the straight line is the same as the slope of the curve, but only at that one point. What if I want to know the velocity at this point up here at t2, or way back down here at t1? Then I would have to draw another tangent line at those points to calculate what the velocity was at t1. I would need another tangent line here at t2 in order to come up with those two velocities. But at any point along this curve, I can draw a line that is tangent, calculate its slope, and know that that is the same as the slope of the curve, and therefore that is the velocity of the object at that point. So with the dt graph, or the displacement time graph, if you want to say the position time graph, it's really just one equation, and that is the x equals 1/2 at squared plus v naught t plus x naught equation. There are no other equations for us to really look at in terms of thinking about the shape of the curve or the slope of this line. We simply look at that equation to express the motion of the object.